Welcome to my channel. In this video, we are going to discuss about some of the questions related with the subject circuit analysis for the preparation of the TRB exam. Okay, so already I posted some 5 videos. If you want to learn that videos means I will give link in the description box. You can refer it. Okay, so all that questions are taken from the previous TRB questions, Polytechnic as well as the assistant professor examination. Okay. The first question you see, a 100 watt electric bulb draws a current I from the 200 volt 50 hertz power supply. The current I is dash. Okay, so the electric bulb of the rating is 100 watts. This bulb draws the current I from the supply voltage is 200 volt 50 hertz power supply. The current I is, what is the thing? Okay, so the 4 option is given. So here, in order to solve that one, first we have to note down the given data. So what are the given data? The power is given P equal to 100 watts and voltage is 200 volt. The frequency is 50 hertz. Okay. Our question is we have to find the current I. So in order to find out the current I, here the power and voltage is given. So already we know the relation, the power P is equal to V into I. Okay, so you know the relation, the power is nothing but it's a product of voltage into current. So from that relation, the P and V is given, we have to find out I. Okay, so after rearranging, the current I can be written as P divided by V. So 100, the power is 100, voltage is 200. So 100 divided by 200, 0.5 amps. So D is the correct option. Okay, then the second question. A resonant frequency in a RLC series circuit draws a maximum current due to dash. Okay, so in series RLC circuit at a resonant frequency, the resonant frequency at resonant frequency condition, the maximum current is flowing in that RLC circuit already, Okay, so because this is the characteristics curve, the current versus the frequency. Okay, at a resonant frequency, this RLC circuit, current flowing through the RLC circuit reaches the maximum value because of what is the reason? Okay, so the first one, the difference between capacitive reactance and inductive reactance is 0. The second option, the impedance is more than its resistance. The voltage across the capacitor is equal to the applied voltage. The PF, power factor, is less than unity. Okay, so in that thing, which one is the correct means the first one. Okay, so at a resonance condition, the capacitive reactance and inductive reactance gets cancelled. Okay, so that's why that is the capacitive reactance value and inductive reactance value magnitude is same, but polarity is different. So that's why that the reactance gets cancelled. So this RLC series circuit, it will behave as a purely resistive in nature. Okay. So because of that one, the current flowing through the series RLC circuit reaches maximum value at resonant frequency. So the difference between capacitive reactance and inductive reactance is 0. So this is the correct option. Okay, so you see this is the thing. At resonance, the reactance of inductance is equal to the reactance of capacitor. So that's why the difference between the two is 0. Okay, and the series RLC circuit, it behave like a pure resistor. That's why the current flowing is maximum. Okay. Then the third question, the superposition theorem is not applicable for dash. Okay, so already we discussed this question. This question is very important and a repeated question. Superposition theorem is applicable for voltage calculation as well as current calculation. Okay, but superposition theorem is not applicable for power calculation. Okay, power calculation, it is not applicable. The next question, the time constant of the network shown in figure. Okay, so this is a one series and parallel RC circuit. So here the two resistance of value, one is R, another one is 2R, and one capacitor C is connected. Okay, in this network we have to find out the time constant. Okay, this is the transient circuit. We have to find the time constant. So this is the 4 option is given. So we know that for RC circuit, the time constant tau is equal to R into C. Okay, the product of R into C, it is nothing but a time constant for one RC circuit. Okay, so here there are 2 resistances is there. So you see, you just check how this resistor connected R and 2R. R and 2R is connected in parallel combination. Okay. So the parallel combination of R to R value we have to calculate. It is said to be the R total. So the R total is equal to R into 2R divided by R plus 2R. So the answer is 2R divided by 3. Okay, so you just substitute this total resistance value in our time constant formula. So the time constant tau is equal to 2 by 3 R into the capacitor C. Okay, so the answer is, so you see 2 RC divided by 3. So this D is the correct thing. Okay, this is the time constant of our given circuit. Then the next question, when a DC voltage of 100 volt is applied to a circuit having resistance R equal to 10 ohms and inductor L equal to 10 Henry connected in series. So the given circuit is a series RL circuit. Okay, one resistor and one inductor is connected. This is resistor R, inductor L is seriously connected with a DC voltage of 100 volt. Okay, so this is the series RL circuit. So in the series RL circuit, the current after 0.1 second, after switching on, the time taken to reach half of its final values are dash. Okay, so here the question is, so what is the current after 0.1 second? Okay, the current flowing through this RL circuit, we have to find out at time t equal to 0.1 second. It is a one question. And the next question, the time taken to reach half of its final value. Okay, so this is the resonant circuit, you know. So whenever the time increases, after one particular time, the steady state current is flowing through this RL circuit. That is the final value. Okay, at a time t equal to infinity, one maximum current, maximum or the steady state current is flowing. So half of the maximum current, in which time it is flowing, we have to find out. So two things we have to find out. In RL circuit, what is the current at time t equal to 0.1 second, and another one, what is the time taken to reach the final value, half of the final value. Okay, the two things we have to find out. So this is our RL circuit with the voltage value given, resistance value given, and inductor value given. So already you know the formula for current flowing through the series RLC circuit. Okay, already we discussed this thing. You just remember it. The current flowing through this transient circuit, RL circuit, is I of t equal to V divided by R into 1 minus e power minus t R by L. Okay, here V is applied voltage, R is a resistance value, L is a inductance value. So you just substitute voltage, resistance, and inductance value here. So V is 100 divided by the resistance 10 into 1 minus e power minus R is 10, L is 10, so 10 by 10 t. So the answer is 10 into 1 minus e power minus t. Okay, this is the current flowing through this RL circuit at any time. Okay, so our question is, we have to find the current after time t equal to 0.1 second. So you just substitute instead of this time t. Okay, at a time t equal to 0.1, you just substitute in the above formula. So I of 0.1 second is equal to 10 into 1 minus e power minus 0.1. So the answer is 0.96 amps. So the current at time t equal to 0.1 is calculated. Okay, and the next thing is the time taken by this circuit in order to reach half of its maximum value. Okay, so first we have to calculate what is the final current flowing through this RL circuit. So in order to find out the final current flowing through this RL circuit, you just substitute time t equal to infinity in our I of t equation. Okay, so this is the current. I of 0.1 means the current at a time t equal to 0.1. Okay, similarly, in order to find out the final value, you just substitute t equal to infinity in our I of t equation. So I of infinity is equal to 10 into 1 minus e power minus infinity. So e power minus infinity value is 0. So I of infinity is a 10 amps. Okay, so the final value is 10 amps. Okay, so what is the half of the final value? So 10 divided by 2, 5 amps. Okay, so our question is to the time at which the current reaches half of its final value. Okay, so in which time the current flowing through this RL circuit reaches 5 amps. Okay, so that's why So here we have to equate. Okay, so we have to find out the T value at the current I is equal to 5 amps. Okay, so that's why we have to equate it. So 5 equal to 10 into 1 minus e power minus 10 by 10 T1. You just rearrange this equation and we have to find out this T1. So here the T1 is nothing but the time at which the current flowing through this RL circuit reaches 5 amps. Okay, so you just rearrange. So 10 you just give to here. So 5 by 10 is equal to 1 minus e power minus T1. Okay, after that you just subtract 1 both sides. Okay, then you take a ln on both sides. Then after rearranging, we can get the time T1 is equal to 0.693 seconds. Okay, so the final answer is current at a time t equal to 0.1 is 0.96 amps and the time taken is 0.693 seconds. Okay, so here you check the options. So here the time is the current is 0.96, time is 0.693. 0.96 and is 0. So A is the correct option. Okay, so this is the thing. So this is the TNEB ECE 2018 question. Okay, then you check the next question. A series RLC circuit contains a 10 ohm resistor and it has a bandwidth of 0.5 kilohertz. Okay, what is the value of inductor L? Okay, in series RLC circuit, resistor value given, bandwidth is given. We have to find out the inductance value. Okay, so for series RLC already you just that is the resonant frequency formula, bandwidth. Okay, the condition value you just remember it. Okay, the resonant frequency omega R is 1 by root LC, you know. Similarly, the bandwidth formula you just remember it. The bandwidth of series RLC circuit is R divided by L. Okay, so here bandwidth is given, resistance value is given. So let us rearrange and we have to find out the value of L. Okay, if you are rearranging, the L inductor is equal to R divided by bandwidth. So R is 10 divided by the bandwidth is 0.5 kilohertz. Okay, so the answer is 20 millihenry. Okay, this is the correct option. So you just remember this formula. Then the next question, the effective inductance of 3 inductors of inductance value L1, L2, L3 respectively connected in series is dash. Okay, so here the inductance L1, L2, L3 connected in series means what is the effective inductance? Effective inductance means the total inductance. Okay, so the total inductance is nothing but addition of L1 plus L2 plus L3. Okay, similar to resistance, if inductors are connected in series means the total inductance value is nothing but an addition of the individual thing. Then the next question, 3 resistors of 6 ohm, 4 ohm, 6 ohm, 8 ohm are connected in series to a 36 volt battery. The potential across the 6 ohm resistor is dash. Okay, so here using voltage division theorem we can solve, or KVL we can solve. Okay, so here what are the things given? 4 ohm, 6 ohm, 8 ohm, 3 resistors connected in series with a battery, 36 volt battery supply is given. So the question is voltage across this 6 ohm resistor. Okay, voltage across the 6 ohm resistor we have to find out. So in order to find out this thing, we can use voltage division theorem. So, you know, in series connected network, the voltages, this total voltage 36 volt is splitted into the potential, the voltages dropped across the resistor depending upon the resistance value. Okay, so according to voltage division theorem, if we want to find voltage across this 6 ohm resistor means that voltage is equal to total voltage. What is the total voltage? 36. Okay, total voltage VT into that particular resistor divided by addition of all resistor. Okay, so here you see what is the total voltage? 36 into our aim is to find voltage across 6 ohm resistor. So 6 divided by addition of all resistor, 4 plus 6 plus 8. Okay, so if you are solving, you can get 12 volt. Okay, so the voltage across this 6 ohm resistor is 12 volt. This is the correct option. Okay, similarly, if you want to find voltage across 4 ohm resistor means 36 into 4 divided by 4 plus 6 plus 8. Okay, so you just use this thing. This is nothing but a voltage division theorem. Then the next question, when a load is matched to the source, the total power supplied by the voltage source Vs is dash. Okay, that is, we studied the maximum power transfer theorem. Okay, if one load, this is the load resistor RL, this is the source means, so in which condition the total power supplied to the load by the source means under the condition of maximum power transfer theorem. Okay, so under maximum power transfer theorem, the maximum power is supplied is Vs squared divided by 4 into Rs. Okay, where Vs is a voltage source value. Okay, Rs is the source resistance. This is the maximum power supplied by the source to the load. Okay, this is maximum power transfer theorem. The next question, the resonant frequency omega naught of a parallel RLC circuit is dash. Okay, so for either for parallel RLC circuit or series RLC circuit, the resonant frequency formula already you know. Okay, it is a very familiar formula. The resonant frequency here omega naught is given. Okay, the radiant frequency, so omega naught formula is 1 divided by square root of LC. Okay, instead of omega naught, if they are asking the resonant frequency in hertz, F naught means 1 by 2 pi root LC. Okay, so this is the resonant frequency formula. Okay, and the next question, any two terminal bilateral linear DC current can be replaced by equivalent circuit consisting of a voltage source and a dash. Okay, parallel resistor, series resistor, parallel capacitor, series capacitor. Any two terminal bilateral DC current, okay, it can be replaced by an equivalent circuit, it consisting of voltage source in series with resistor. Okay, so already we studied that current source to voltage source transformation, voltage source to current source transformation. Okay, so in that, any current source in parallel with resistance, we can replace it with voltage source in series with the resistor. Okay, so that is a concept here. In the next question, find the current I. Okay, this is a given circuit. In that, we have to find the current I value. Okay, so this is the current I. The current supplied by this 8-volt battery. This is the current I. We have to find out. So you check the circuit here. This is the 1 amps current source. This is 2-volt battery, 8-volt battery. Here one resistance is connected. Okay, so here you just mark the branch current. So because of this 1 amps current, the current flowing in this branch is 1 amps. Okay, and you just take the current flowing, the current supplied by this 8-volt battery, you take it as a I. Okay, so then I is coming here, 1 amps is coming here. So what is the current flowing through this resistance? It is an addition of the two thing I plus 1. Okay, so our aim is to find out the current I. Okay, so in order to find out the current I, you just apply KVL, Kirchhoff's voltage law, to this loop 2. Okay, you just apply Kirchhoff's voltage law to this loop 2. So if you are applying, first you see minus to plus, it's a voltage rise, 8 equal to I plus 1 into 2. It's a voltage drop, plus this is also the voltage drop. Okay, so 8 equal to 2I plus 2. Okay, 2I plus 2 here. So 8 minus 2, it is 6. Then 6 minus 2, 4. So after rearranging, we can get the current I is equal to 2 amps. Okay, so the current I is 2 amps. This is the correct option. The next question, a parallel RLC circuit has R equal to 10 kilo ohm, L equal to 10 millihenry, C equal to 1 microfarad. Find omega R and quality factor. Okay, so for series RLC circuit, RLC is given. We have to find out the resonant frequency and quality factor. Okay, so already you know the formula. The resonant frequency omega R is nothing but 1 by square root of LC. Okay, so 1 by square root of L is 10 milli. So 10 into milli means 10 to the power minus 3. Capacitor C is 1 microfarad. So 1 into 10 to the power minus 6. Okay, so you just substitute it and the answer is 10 to the power 4. Okay, then quality factor. So quality factor, this is a parallel RLC circuit. So for parallel RLC circuit, the quality factor Q is equal to omega R RC. Okay, so the three different formulas that this is one of the formula, omega R into C. So omega R is 10 to the power 4, resistance value is 10 kilo ohm. Then the capacitor value is 1 into 10 to the power minus 6. Okay, so if you're solving, you can get the answer 100. Okay, so these are all the formulas, you just remember it. Then the next question, the delta connection draws dash of the current of star connection. Okay, delta connection draws dash of the current of star connection. 1 by 3, 3, 2 by 3, and 1 by 3. Okay, you know, if in delta network, okay, the impedance in delta network is nothing but 3 times the impedance of star network. Okay, the impedance in delta is 3 times the star impedance. So that's why the current supplied is 1 by 3 times. Okay, this is the thing, 1 by 3. The next question, the degree of node for node 4 in the graph shown in figure. So you see, this is the given graph. In that graph, these are all the nodes, node 1, 2, 3, and 4. So the question is, what is the degree of node 4? Okay, for this node 4, what is the degree of node? So already you know the definition, degree of node means number of branches connected to that particular node. So how many branches connected? This is 1, 2, 3. 3 branches connected. So the answer is 3. So 3 is the correct answer. Okay. So in this video, we discuss some 15 questions. So, okay, so we will discuss the remaining questions in the next video. Okay, so thanks for watching my channel and please subscribe my channel for more videos. Okay, so I will give link for the other TRB circuit analysis questions in the description box. You can use it. Okay.